Greetings students and welcome to the 9th Logic Lecture of Comp 0003. Today we're going to begin our third main topic, which is proof by induction. You may have come across proof by induction over natural numbers in high school mathematics, but here we're going to think of it in a more general sense. So in mathematics, and very often as well in computer science, we can define objects inductively, or sometimes we also say recursively. In other words, we say what are the smallest or atomic objects of that data type, and then we give some operations for constructing larger data from smaller ones. So we've already seen some examples of this in the course already. For example, when we defined formulas in propositional logic, the smallest formulas are just propositions, and then we have the connectives for building up larger formulas. And the same, of course, is true in first order logic, except that our smallest formulas, our atomic formulas, are their predicate formulas, and then we have connectives and quantifiers for constructing larger ones. We've also seen the example of terms in first order logic, where the smallest terms are either variables or constants, and then we can build up larger terms by applying the function symbols. But there are more examples as well. So for example, either when we think of natural numbers in mathematics, we can think of natural numbers as being generated by an inductive definition where 0 is the smallest natural number, and then to construct a larger natural number from one that we have already, we just apply the successor operation to get the next one. A very similar kind of definition will get you the idea of a list. The smallest list is the empty list, and then we can construct larger lists from smaller ones by concatenating an element onto the front of it. And the same is true for trees as well, where a single node by itself is a tree, or we construct a larger tree from smaller ones by adding a parent node and joining on the children. So that then leads us to the idea of proof by induction. So supposing that we have some inductively defined data where we have some kind of smallest or atomic data and some construction operations for constructing larger ones, well then how do you show that all objects of that data type have a certain property? Well, you should show that the property must be true of the smallest data of that type, because if it's not true of the smallest data, it's certainly not true for all the data. And then you show that supposing that the property is true of some arbitrary data of that type, and you apply a construction operation, then the property is true as well for the larger object constructed using that operation. And then it follows that any data you can build using the operations must enjoy the property. So today we're just going to cover the case of the natural numbers, which is the simplest case that you may have also encountered at the high school level. Accordingly, this might be quite a short lecture, but I think it's useful just to kind of cement the concepts and make sure that we're all in the same place. So without any further ado, let's now go to the slides, and as always, I will see you again at the end. So before we begin in earnest, I think it's useful just to get a high-level overview of the situation. As I said, today we're going to begin looking at proof by induction, which is a technique for establishing a universal property of inductively defined mathematical structures or data. So we mentioned some examples of inductively defined data or objects or structures at the beginning there. So they include, for example, natural numbers, lists, trees, formulas of different kinds, terms, and so on. An inductive definition always has the shape of saying, first of all, what are the smallest objects of a certain type, and then also how it is that we're allowed to build up larger objects of that type from smaller ones. Now, that means that whenever we have a structure or class of structures that has been defined that way inductively, then we also get for free somehow a principle of induction for showing that all objects of that type have a certain property. Namely, we have to show that the smallest objects of that type have the property, and that if some arbitrary element, structures of this type have a property, and we apply the construction operation to get a larger object of the type, then the property is true for the larger structure as well. And then it follows that the property must hold for all structures of that type, because you've shown that the property holds no matter how it is that we build up the structures. In the next 3 or 4 lectures, I think we're going to see quite a number of different induction principles. Not only different induction principles corresponding to different inductively defined structures, but also different induction principles even on the same structure. But it's worth saying that for the most part, all the induction principles that we will see over any given structure are going to turn out to be equivalent to one another. In today's lecture, though, we're just going to start with the most common form of induction on the most commonly inductively defined structure, which is the natural numbers. Now, before we go and do any proofs by induction, I wanted to just make sure, especially because high school mathematics tends to focus much more on calculating things than proving things, which I disapprove of in principle. I think it's just as important to understand why things are correct as just remembering that they are correct and applying the method. So I think it's a good idea for us to do a very simple proof just to get warmed up and to make sure that we are all on the same page regarding basic proof technique. So by a universal property of something, I mean something that's of the type, for all things of this type, this proposition holds. So here's a very simple lemma. I mean, it's kind of trivial, really. The sum of any two even numbers is even. So I can write that in first order logic using a predicate for being even and a function symbol for sum. So I say for all n and m in the natural numbers, even m and even n implies even of m plus n. So that's a kind of formal way of writing that down. By the way, this here is technically not part of first order logic because we're kind of using some abbreviations here. So really this is two quantifiers for all n and for all m. So that's the first part of abbreviation. And then, of course, there's this part here that says in the natural numbers. Now, you can think of this, if you want to think of it kind of formally, as kind of saying either that we are thinking about some first order structure whose domain is the natural numbers, and that means that all the objects in the universe are of that type. They must range over the domain. Or you can think of it as saying somehow we have another predicate standing for the property of being a natural number, and this is really abbreviating for all n, for all m. If n and m are both natural numbers, then the following thing holds. Anyway, I mean, the point is that this means exactly what you think it does. It says whenever n and m are natural numbers, m and n are both even, then their sum is even as well. So, in order to prove a universal property of, in this case, natural numbers, well, I should consider two natural numbers, but I can't pick specific ones. I have to show that it's true for all natural numbers. So I can pick two natural numbers, but I can't assume anything about them other than that they are natural numbers. I can't say take 12 and 14 because that is not showing anything universal. If you want to show a universal property of something, you have to pick some arbitrary element from the set and not assuming anything special about it and show that the property is true in that case. So I'm going to assume that we have two numbers m and n which are in the natural numbers, and then I have to show an implication that if m and n are both even, then so is their sum. So if I want to show an implication, A implies B, you could remember from the truth table that the implication is automatically true in the case where A is false, so we don't worry about that case. We don't have to worry about the case where m and n are not even. We just have to worry about the case when they are. So let's suppose that the left-hand side of the implication holds, which is to say that m and n are both even. Now we must show that the right-hand side of the implication holds. So to show an implication A implies B, the strategy is always assume A and show B. Although I should say, perhaps not always. Always, you could also proceed by assuming not B and go on to prove not A. But we're not going to do it that way around today. So let's assume two even numbers, m and n. Now, by definition, being even is the property of being divisible by 2. So that means that m is equal to 2m prime and n is equal to 2n prime for some numbers, some m prime and n prime, which are both natural numbers as well. Then their sum, of course, is just by replacement 2m prime plus 2n prime. And by taking the common factor, this is equal to 2 of m prime plus n prime. And that means that m plus n itself is also divisible by 2, and therefore it's even. And this completes the proof. So now time for a little bit of history and context. This chap in the picture here is Augustus de Morgan, he of the De Morgan laws, which we saw when we studied propositional logic. And he was a professor of mathematics, in fact, here at UCL in the 19th century. And he was also the first person to identify induction as a standalone principle of mathematics. In fact, when I wrote my own PhD thesis in Edinburgh back in the early 2000s, I studied induction and inductive methods. That was my speciality. And I went to the library in the University of Edinburgh. I went to the special section where they keep all the old and rare books, and you have to have special gloves to handle them and this kind of thing. And I leafed through these very old encyclopedias and found this original entry on induction, which was by Augustus de Morgan. So it starts by saying the method of induction in the sense in which the word is used in natural philosophy is not known in pure mathematics. So here, when he says natural philosophy, he actually means what we might think of as science. And in science, say physics or chemistry or something, or indeed more generally in philosophy, induction describes the process of drawing a generalization from a hopefully quite large number of observations. So, for example, if you were dropping stones off of the Leaning Tower of Pisa, and you dropped them all at the same time, you would observe that they all hit the ground at the same time. And so you might sort of draw the conclusion inductively, as it were, that since it's happened all these other times, that any further stones that you drop off the Tower of Pisa will also hit the ground at the same time. And then you might go on to sort of theorize the existence of some force, such as gravity, that is kind of making that happen. It's not a logically valid way of reasoning because, of course, just because something has been observed a large number of times doesn't mean it will also be observed any subsequent times. One famous example of this is the so-called black swan phenomenon. In Europe, for a long time, it was believed that all swans were white. They all had white feathers because nobody had ever seen a swan that was not white. And of course, people were surprised when they visited, I think, Australia for the first time to discover that there were also such things as black swans. Similarly, you might think that because the sun comes up every morning, that you might be forgiven for thinking that the sun will therefore come up every morning. But of course, at some point after many billions of years, the sun will die, and that will no longer be true. Or you can think of the turkey who gets fed by the farmer every morning until Christmas time comes around, and then he comes with a big old axe or something like that instead. So, to continue the quote, there is, however, one particular method of proceeding which is extremely common in mathematical investigation, and to which we propose to give the name successive induction. Nowadays it's just called induction or sometimes mathematical induction. It has the main character of induction in physics because it is really the collection of a general truth from a demonstration which implies the examination of every particular case. But it differs from the process of physics in as much as each case depends on one which precedes. And so this is in this penny cyclopedia from 1838. So mathematical induction is still, I mean, it's like induction in physics because it involves drawing a generalization. So you're deducing a general statement about something, but it's different from science because in mathematical induction you have a guarantee that you're covering every possible case. So now let's give our first inductive definition, which will be of the natural numbers. So, you know, in school, of course, we're just told that they are 0, 1, 2, 3, 4, and so on. We learn how to count, but they can also be defined inductively in the following way. First of all, 0 is a natural number. So this is it is the smallest object of that type. So it's the kind of base case of the definition, if you want to call it that. And then if n is a natural number, then its successor, s of n, is also a natural number. Sometimes this is called a step case of the definition because it explains how to build a bigger object of the type given some existing number. And also, although we usually don't bother to say this when we're making an inductive definition, nothing else is a natural number other than those that are given by the two above rules. So 0 is a number, and for any number, then its successor is a number, so that gives us the successor of 0, which is 1, is a number, and successor of 0 is a number as well, and so on and so forth, but nothing else is a natural number. By the way, you can also see these as terms in first order logic where we have a constant 0 and we have a function symbol s, which is unary. And so then it's like taking terms in a language where we just have one constant and one function, which is s. So you can see how we might sort of exploit this to prove a property. If we want to show that something is true for all numbers, well, if we need to show that it's true for 0, because if it's not true for 0, then it's definitely not true for all numbers. And then if we suppose that a property holds of n and show that then the property must be true of Sn, then we know that since the property holds for 0, it must hold for S0, and then it must hold for SS0 as well. And so we will get to the property holding for all numbers somehow by kind of knocking them all down like dominoes. So now I'm going to give a formal statement of the principle of mathematical induction on natural numbers. So let's assume that we want to prove some universal property P of natural numbers. So P is some property. So you can think of it as being a predicate perhaps, or a formula with a single free variable. And we want to show that this property P holds for all natural numbers. So we're going to proceed in the following way, remembering that a number is either 0 or the successor of something which is already a natural number. So first of all, we must show that P holds of the number 0. Now this is called the base case of the induction. Certainly, if P is not true of 0, then it's not true of all natural numbers. So at least we have to show that it is true for the smallest number. The next step is to assume that P holds for some arbitrary natural number K. And this assumption is called the induction hypothesis, or IH for short. And so we're going to make that assumption. We can't assume anything about the number K other than it is a natural number. Lastly, using this assumption, we have to show that P holds for the successor of K. Now, showing that is called the step case of the induction. Having carried out these three steps, we can conclude that P must hold for all natural numbers. Why? Well, because any number is either is either 0 or the successor of another number, and we know that P is true of 0, and since it holds of P 0, and we know that if it holds of any number K, it must hold for the successor of K, then we know that it must hold for the successor of 0. Since we know that it holds for the successor of 0, and that's a number, then we know that it must hold for the successor of 0, and so on. So we kind of knock them all down, as I say, kind of Pokemon style, catching them all. And here's just the principle, these 3 steps written as a single inference rule. So we have 2 premises, which I'm writing above the line, and then our conclusion, which is below the line. So the first thing we have to establish is that P holds of 0, the base case. The second thing to establish that if P holds of K, then it holds for the successor of K, where K is some arbitrary number, so we can't assume anything about it. And then the conclusion is that P holds for all natural numbers n. Let's see an example. So let's take a nice simple example. A universal property of natural numbers is that all natural numbers are either even or odd. Now, written down as a first order logic formula, where I'm kind of also specifying the domain here, that's a statement for all n, even n or odd n. Now, the proof is going to be by mathematical induction on n, and the first thing we have to do is establish the base case. By the way, you will definitely be asked to construct proofs by induction, both in the exercises and in examination situations, and I would like you to set out your proofs in roughly the same way that I'm doing here. So, just as one note, our property of natural numbers is the property of being either even or odd. So Px equals even x or odd x. So the base case of the induction is that we have to show that P holds of 0. Now, just by substitution, this means showing that 0 is even or 0 is odd. Now, of course, 0 is an even number, and therefore it is definitely even or odd, so P holds of 0. And that's the base case taken care of. Very easy. Excuse me. Now, the next thing we have to do is make our induction hypothesis. That's the kind of second step that we laid out before. So that means assuming that P holds of some arbitrary natural number K. Just by substitution again, P of K is even K or odd of K. So let's assume that K is either even or odd. That's exactly what P of K says. Now what we have to show is that the successor of K is then either even or odd as well. So the step case is we need to show P of S of K, and that means showing that the S of K, successor of K, is either even or odd. Now, there are actually 2 cases to consider. We know that K is either even or odd by the induction hypothesis, and so let's consider the 2 possible cases separately. On the one hand, let's suppose that K is even. Well, in that case, it must be that successor of K is odd, and therefore it's also even or odd, because the successor of any even number is always an odd number. On the other hand, if K is an odd number, then S of K is even, because the successor of any odd number is even. And so either way, we know that K is either even or odd by assumption, by the induction hypothesis, and whether it's even or odd, its successor must also be either even or odd. And so we're finished. That completes the induction, and the conclusion is, by induction, that P of n holds for all n, which is exactly this statement here. For all natural numbers n must be either even or odd, because it's true of the smallest number, and given that it's true of some arbitrary number k, it's true of the successor of that number as well. So as our next example, let's take the following inductive definition of the addition function on natural numbers. So I'm defining plus by these two equations displayed here. And it's actually by induction on the left-hand argument of the addition. So the first equation, which I'm labeling number 1, says that 0 plus y is equal to y by definition. And the second clause says that if I'm adding the successor of some number to y, s of x plus y, then that is equal to the successor of x plus y. Now, you can notice that this is an inductive definition because here I'm assuming that I already know what x plus y is, and then I define what successor of x plus y is. So it's defined by induction. It's by induction on its left-hand argument. You can see there are two cases. A natural number is either 0 or the successor of some number. So we have a case for 0 and the case for another number. Now let's prove a lemma about this definition. So the lemma is that for all natural numbers y plus 0 is equal to y. Now notice that this is not immediately implied by equation 1 because that says that 0 plus y is equal to y, and it's not obvious from this definition of plus that it is commutative. In fact it is, and we will show that, but for sure it's not immediately obvious and you have to prove it. So let's proceed, unsurprisingly, by induction. There's only one variable in the lemma statement, so we don't really have any choice. We have to go by induction on y. So here, p of y is the formula y plus 0 equals y, and we want to show that this is true for all numbers y. So this is the statement that we're trying to prove by induction. Now, as before, we have to show that the base case of the induction holds, which means showing that p is true of the number 0. Now, just by substituting 0 into this formula for y, that means that we have to show that 0 plus 0 equals 0. And that is true immediately by equation 1. It's an instance of equation 1. For our induction hypothesis, we have to assume that p holds for some arbitrary natural number. So we'll take out this arbitrary number to be k, and we're going to assume that p holds of the natural number k, which means exactly assuming that k plus 0 is equal to k. Then for our step case, what we have to show is that p is true for the successor of k. So that means showing that the successor of k plus 0 is equal to successor of k. So we're going to use equation 2 and the induction hypothesis. We have to show, so let's start with successor of k plus 0. By equation 2, that is equal to successor of k plus 0. That's just an instance of this equation here, number 2. And then we know that k plus 0 equals k by the induction hypothesis. So that means that this is exactly equal to the successor of k. And that is exactly p of s of k. So by induction, we conclude that p holds of all natural numbers. In other words, y plus 0 equals y for all natural numbers y. Okay, now let's move on and think of an example that doesn't look a lot more complicated, but actually really is. This looks like a simple statement, it looks like a simple property, but it's actually not so obvious. For all natural numbers x and y, x plus y equals y plus x. Now that means that plus is commutative. That's what I mean. That's what it says. But again, we have to prove it. Now we have a choice here. We could proceed by induction on x or by induction on y. But since this equation is completely symmetric, in fact, the choice is not going to matter. So let's choose to go by induction on x. And that means that because there are two quantifiers in this lemma, it means that our px is actually a universally quantified property over y and still has the free variable x. So if I kind of strip the x quantifier off this statement, I still have a universal quantifier over y. So p of x is the property that for all y, x plus y equals y plus x. So again, just the lemma statement. And you can show that, and you can see that if I can show this for all x px, then I'll get back exactly this lemma statement. So in the base case, we have to show that for all y, 0 plus y equals y plus 0. Now, fortunately, we are done by the previous lemma, and I guess by equation 1. So equation 1 tells us that 0 plus y equals y, and our lemma tells us that y plus 0 equals y as well. So that's the lemma on the previous slide. So the base case is taken care of. Now, the induction hypothesis is that for all y, k plus y equals y plus k. In other words, p of k. So again, we're just assuming that p holds for some arbitrary natural number. And we have to show that for all y, the successor of k plus y is equal to y plus the successor of k. So that is, again, it's just exactly p of s of k. We haven't had to think about that or invent anything. We're literally just substituting the term successor of k into the property p. So let's just assume some arbitrary y. We can't assume anything about it. And then let's start at the left-hand side of this equation and see how far we get. So using equation 2, successor of k plus y is equal to the successor of k plus y. And by the induction hypothesis, k plus y is equal to y plus k. And then I guess we can also apply equation 2 again to get that this is equal to the successor of y plus k. But we're actually kind of stuck now. We have to show the successor of k plus y equals, we have to show that successor of y plus k is equal to y plus successor of k. So we can kind of transfer the successor from the left-hand side to the right-hand side of plus. But actually our equations and our induction hypothesis doesn't give us any way of doing this. Now, quite often, when you get to this point where you're really stuck, you can't see how to proceed, you need a lemma, but you don't actually have it, well then you might just say, well, let's try, we don't know that it holds, let's try and prove that it holds. So this will actually become another induction, which leads us to our last example, which is to say that for all y and k, successor of y plus k equals y plus the successor of k. Now this is exactly what we need to finish the step case of the previous lemma. So let's try and prove it. I'm going to proceed by induction on y. I think here, actually, I do have a choice. I could proceed by induction on y or by induction on k. But actually, proceeding by induction on k is not wise. And the reason is that you can see that plus is defined by induction on its left-hand argument. So you know that when we do induction on y, we're going to get a 0 case, we're going to get successor of 0 here, and we're going to get 0 here. We're going to be able to do something with it. Whereas if we have a 0 on the right-hand side, or a 0 on the right-hand side here, it might be harder to do anything with it. Although maybe not. And you could try doing this by induction on k as well. But I'm going to choose to try by induction on y because I know it's going to work. So the base case, here our p is sy plus k equals y plus sk. And that's for all k because we're going by induction on y. So in the base case, we have to show that for all k, successor of 0 plus k is equal to 0 plus the successor of k. Now, that's quite easy to show using equations 1 and 2. It can be like a little exercise. It's very easy. So you can check that for yourself. The induction hypothesis, I've already used the variable k in my lemma statement, so I'd better not use it again here now. So instead of making the assumption for an arbitrary number k, I'm going to choose the name z instead. So I'm assuming p of z for my arbitrary z, which is for all k, successor of z plus k equals z plus successor of k. So that's the property with z substituted for that y. And we have to show that p then holds of the successor of z, which when I substitute in, again, putting successor of z in for y in this equation, this means showing that S of sz plus k equals sz plus sk. Now for this, you're definitely going to need equation number 2, and you're going to need the induction hypothesis as well, and finishing that step case is an exercise. So I think it should be quite straightforward to do. I do encourage you to have a go at it. And then just to remark again that with this lemma here that we show, this is exactly what we need to complete the step case of the previous example. We'll just go back to it again. So the lemma is that successor of y plus k equals y plus successor of k. If we keep track of where we had to go back to, in the step case of the induction, we had to show that successor of k plus y equals y plus successor of k. We managed to get as far as showing that the left-hand side is equal to successor of y plus k, and then by the lemma that we have that I've asked you to finish proving as an exercise, this is equal to y plus sk, and then we're done. And I think that's a good place for us to stop for today. In the next lecture, I'll go on to describe induction over structures other than the natural numbers. So we'll look at induction for lists and trees and perhaps some other things too. So thank you for your attention today, and I will see you again very soon.